Hey, good morning everyone. It's Miss Packard. I hope you're doing well and staying safe. Today we're talking about why are logarithms important. So I know a lot of you always ask this question. It's like, when are we ever going to use this? And the cool thing is that you're actually using logarithms quite often nowadays when looking at data. So the objective today is that we're going to be able to identify the scale of a graph and describe why scale is important. So we have that distinction between a logarithmic scale and a linear scale. That's what we're going to talk about. We've got the video today, and then your classwork grade is going to be a Google form that's going to ask you to identify whether or not the scale is linear, exponential, or logarithmic, and why scale is important. All right, so first off, our definition of scale is going to be the set of numbers used to measure or quantify objects, right? So sometimes we say, oh, I'm drawing this like to scale. That means I'm drawing it the actual size it is. But sometimes if you draw a picture of a person on a piece of paper, it's much smaller than the actual person would be, right? So you've scaled that down. But when we talk about graphs, so scale on a graph, I'm going to say on a graph, we're going to be specifically looking at the axis labels. And I'm going to give you some examples. Take a minute to write this down if you need to. You can pause the video. So on this graph, first I'm going to label my x-axis, my y-axis. I'm going to look at the scale. So let's start with the x-axis. This counts 2, 4, 6, 8, 10. And if I look at each tally, it looks like we're going up by 2 each time. So we could say the scale here is linear, and we are going plus 2 each time. This should look like an arithmetic sequence that we learned about last week, right? So since we have this constant plus 2, plus 2, plus 2, the scale is linear. On my y-axis, as we increase going up from 5, 10, 15, 20, 25, we are again adding a constant each time, plus 5, plus 5, plus 5. So we have a linear scale again. I'm going to write this sideways just so that it fits. We have a linear scale, and we could say of 5. Scale is linear by 2 each time. Okay. Now, specifically, we're going to see how this relates to exponential and logarithmic functions. So, when I have an exponential function, this is going to be my first example where I have a table of values. And if I'm looking at this similar to how we did our geometric values, I'm seeing, okay, each value, it's not increasing linearly because it's not adding a constant each time, because this would be plus 1, then plus 2, then plus 4. So that's not the same constant. So what's really happening here is we are multiplying by 2 each time. So we see this set of values is a geometric sequence, which will result in an exponential graph, right? So what I'm going to do first is I'm going to label my axes, because I've got these tick marks, but I don't really know what they are yet. So I'm going to label them 1, 2, 3, 4, 5, 6, 7. This is linear because I'm simply adding each time. Same thing on this side. I'm going to go 1, 2, 3, 4, 5. And if I kept going, it would be 6, 7, 8, 9, 10. So I'm going to mark the 10, 11, 12, 13, 14, 15, I'm going to mark the 15. So even though I skipped numbers here, since I still have those tick marks, this is still linear, right? I could fill in each number and have each tick mark adding by 1 each time, right? So this is also linear still. Now I'm going to graph my points. So my first point is 1, 0.5, then 2, 1, 3, 2, 4, 4. We're starting to see that exponential graph. 5, 8, 6, 16. Now that's almost off my graph. And I can't even put 732 on this graph because my highest value here is 15, and then I went one more to 16. So we run into this problem. When I'm trying to graph my exponential function, I can only go so high. And if I wanted to, I can connect all my points and have my nice exponential graph. All right. So we run into the problem that we can't fit on this last point. So the way that mathematicians do this is they change the scale. Specifically, we're only going to change the y-axis. So we're going to take the exact same data, which I've written again here, and now we're going to use a logarithmic scale on the y-axis. So I'm labeling my x-axis the same. So this is still linear on the horizontal axis. But my vertical axis, or my y-axis, I can make this a logarithmic scale by using or taking the log of different values, right? So if I were to say we have 2, 4, 8, 16, 32. If I went like that, then what's happened, instead of each of these values, which were originally these values were 1, 2, 3, 4, and 5. Now we have each line representing one of these exponential values of 2. So I'm multiplying by 2 each time. But the reason this is called a logarithmic scale is because if I took the log base 2 of 2, that would be 1. If I take the log base 2 of 4, that would be 2. The log base 2 of 8, that would be 3. You get the idea. This is what we were doing yesterday. So whatever the value I got as my logarithm value, that's the line or the tick mark that I'm placing my inside value as. So the values that I'm using are 2, 4, 8, 16, 32. This is going to be my logarithmic scale. We are multiplying each time. We have a logarithmic scale. Now when I graph my exponential data, and I graph the point 1, 0.5, I know that's going to be somewhere down here. 2, 1, 3, 2, 4, 4, 5, 8, 6, 16, and 7, 32. What happened to my exponential graph is since I fit this to a base 2 logarithm, I end up with something that looks a lot more like a line. So especially this part here is very linear. So what I've done is I've fit the data. Because I've fit this data to a graph where all of the data fits for one, but we have scaled it down using a logarithm. and made a linear model from an exponential model. So this is something mathematicians do all the time. So what we are going to be doing today is determining, is the scale linear or horizontal on the horizontal axis? Linear or logarithmic on the horizontal axis, linear or logarithmic on the vertical axis, and seeing, does this graph look like a line or does it look like an exponential graph? Okay, go back, watch that again if you need to, because I know I went through that kind of fast. We got one last example before we have our classwork. So this is another example of what I'm going to call a logarithmic scale. If you'll notice, each time I'm increasing on the y-axis, I'm multiplying by 10, right? So in your classwork, I'm going to ask you, is the vertical axis linear or logarithmic? And you're going to say this is logarithmic. On the horizontal axis, each mark here is increasing by 5, or each number is increasing by 5, but each mark is increasing by 1. Either way you justify it, this is still linear. And one more time, to talk about that logarithmic scale, just as another example, if I said this was 1, 2, 3, 4, 5 in terms of the marks, I've adjusted this to be linear. And that's how I'm going to get my values that make this a logarithmic scale, because the log, and this is going to be a logarithmic base 10 scale. And it does matter what the base is, right? So on my other example, I really should have said this is a base 2 logarithmic scale before, because I have a log base 2 here. And it does make a difference, right? So now that I'm looking at my logarithmic base 10 scale, I can say because the log base 10 of 10 equals 1, because the log base 10 of 100 equals 2, because the log base 10 of 1,000 equals 3, and so on. That would continue all the way up. So in your classwork, you'll be doing multiple choice, linear, exponential, or logarithmic are going to be your options in terms of scale and shape of graph. Please let me know if you have any questions. Don't forget, I have office hours every day, 11 to 12. So that's 11 a.m. to 12 p.m. All right, and feel free to send me an email, a comment on Google Classroom, or text me if you need any help. Have a great day. See you later.